Yes. So today I am going to talk about topological phases and quantum computation. Actually, this is the title of a paper by Kitaev and someone I forgot. So anyway, this paper is very extremely important for topological quantum computation. So I'm going to talk about why topological quantum computing can give us benefit and how Kitaev uh predicted. Yeah, this is content. So this paper is has five main contents. The first, introduction. Second is about 1D superconductor, and third one is about toric code, the two-dimension toric code, which you guys might be familiar with. And fourth is about the anyons, and fifth is about the honeycomb lattice. So it's more about application. So anyway, we're going to start from scratch. Okay. 네, 생각나요? Yeah, yeah, sorry. So, uh, as you know, for 어? 화면 공 디스크톱으로 네, 됐나요? 네. So, as you know, we want to avoid quantum decoherence, right? So, uh, for good reason, these two qubit states are degenerate states. They're almost degenerate states, and we want to keep it almost degenerate state and keep it uh not to be excited using this gap. So we are going to our ultimate goal is to make some kind of protective qubits, and we want to avoid uh quantum decoherence. That is just Schrödinger equation. Yes. So what I want to talk about is these two systems. We're going to look about some example and see how topological quantum computing is good. So before topological quantum computing, people use symmetry, something like SU2 symmetry, to protect the degeneracy of energies. But Kitaev is first to mention that you can use topology to keep the degeneracy. So we are going to look at the mathematically equivalent system, but physically different system, and see which one is topologically safe or not. So the first one is transverse field Ising machine, and second one is spin polarized 1D superconductor. So since it's a superconductor, there is a Cooper pair term, as we learned from past journal class. So let me explain. So actually, I can explain the two dimension, but for simplicity, I will for one dimensional first, and this is talking Hamiltonian term. So which means this is emulation and this is creation operator. So you mean you emulate fermion at particle here, fermion particles here, and you make a J side. So it's 1, 2, 3, 4, and N side. So you're making a fermionic particle here. So this is making and um, animating. And this one is about the Cooper pair. So since it's a superconductor, it's a Cooper pair just for humility. Okay, and this is chemical potential term. So this one is actually very important term because uh, what's very special about 1D superconductor is there is a Majorana mode at the edge state of the at the um uh, at only at these the two has some unique property because when the chemical potential gets stronger, the interaction between these are very strong. So as conclusion, they are all bonded, but these two remain. So that's why we are making this kind of open boundary model. And this is fermionic parity operator. So actually, these two commutes. It's important thing to know. And for transverse field Ising machine, there is a spin at the x direction, and then we go the transverse field with this direction, and then we will try to see how it's aligned. So this is basically this are Pauli matrices, and they just represent the total energy of this PFIM. So basically, they are mathematically equivalent because they have same Z2 symmetry. So, however, there is important part because what it means by physical difference is if you just simply add some magnetic term at this Hamiltonian, it's easily break. So in nature, so you can. It is really hard to find this PFIM in nature. However, in physics, it is very likely, or people are just looking forward to look for this one. Since this one's very topologically vulnerable, so we're trying to find this one. So that's the main reason. So this is nothing but just a 2D version of the uh, SPSC. So as you can see, there's nothing much special, but it's just adding more terms with the y directional term. So actually, what we do in quantum matter physics, like I think quantum matter physics has a lot to do with quantum information these days. So I think it's really important to understand some of the Hamiltonians here. So you can actually understand, yeah, this is what I just mentioned. So it's just creation and annihilation operators of the Hamiltonians. So it happens same for the with the y directional term and also the chemical potential term. So as you all know, this one is the number operator, which counts the number of the particle atoms. So because so actually one thing I need to mention is if you check out this parity operator, you can see that its parity is conserved because it's number operator, right? So actually we call this BDG Hamiltonian, and I don't know how to pronounce it well. Maybe Minzu. Yeah. Yeah, that one. So yeah, we can solve it using Fourier transformation, and solving it yes, we can solve using this kind of it's just Fourier transform. Using it, you can solve it. Yeah, I'll just pass. Um, yeah, it just see the conclusion is this whole process is just to get this relation. This is the Majorana operator. So I was just very uh I am thinking about Majorana operator for a long time. I don't know what it is. Oh, but anyway, the interesting thing is when you just solve this Hamiltonian, you can have uh, uh, this kind of uh, term. And so you can see that some kind of P-wave superconductor properties are shown. Yeah. And also, I want to mention something about Chern number, which is the topological invariance. And at K space, if you change K infinitesimally and change the NK vector to that part, then if you do the line, the contour integral, then you can get the winding number, which is very related to topological order. And here, this is something that you can get when you have numerical calculations. And you can see that we can get some, so there is some kind of topologically shifted, the space is shifted. Yeah, so anyway, I just wrote this to kind of explain you can solve this kind of Hamiltonian, and there is Majorana operator. Yeah, so back to the paper. There is a Majorana operator, and Majorana operator can be defined like this. So this is just annihilation and creation operator, and this is the definition, and that is the property. Yes, and using this kind of operators, we're going to change these operators to this kind of Hamiltonian. So we have Hamiltonian back slide, and we are going to change the animators to this kind of Varana operators. Then you get this, and also for the parity, you can change it. So the main result of changing this is because when you say V is 0 here, then the boundary pair C1 and C2 and degenerate. So this is still the 1D system. So the 1 and 2n will degenerate. That is okay. But if you assume this, then this can be replaced by this kind of new operator. So I think the paper is mainly about changing the mathematical forms into various kind of useful and convenient operators. So as a result, the Kitaev gets that kind of effective Hamiltonian. And the important part is that the ground state degeneracy is listed by only an exponentially. So this exponentially small shifting is that epsilon. Its epsilon gives the exponentially small splitting in the system side. So this is important because at the introduction, as I mentioned, it is important to not change the degeneracy, and the topology is actually helping yeah, this kind of system is helping to get the exponentially small splitting for the whole system. So I think that is for the second section of this paper. And also Kitaev brings another Hamiltonian. So he again changed the form to quadratic fermionic Hamiltonians, which looks like this. So the term of 4 over I is retained by this anti-commutation rule. And this is the skew symmetric matrix. So you get this kind of form. So you just change before this Hamiltonian into this kind of form. And then you can solve it. Then you can get the eigenvalues. And what's very important is that if you if we let the epsilons are zero, then it is very important. Um, it has important meaning because it becomes the zero mode has important meaning because if the this is the conclusion. So if the pair of Majorana corresponding to zero modes are physically well separated, we expect perturbations have trouble lifting the boundary degeneration. So this just means that zero mode, uh, if zero modes are physically well separated, then it's very topologically safe. So, so next, actually, it took a long time for me to understand here. But anyway, why the main reason why I wrote this paper is I was actually interested in the chapter 3, the toric chord part, but I wasn't I lack of time. I just stopped there. But actually, why I got interested in the toric chord part is because of the neutral atom quantum computing. So I yeah, so you might be surprised. So I am currently interested in neutral atom quantum computing and also as well as other quantum computation platforms. But neutral atom computing was an underdog for many years. So basically the winning platforms seem to be like the superconducting qubit circuits or ions. But recently, the neutral atom quantum computing has developed to the high fidelity era since 2020. So this is very important to us, I think. And so, which means it can be combined to multi-qubit arrays and build a quantum computer. Yes. So those two Nature papers were all published in 2022. So fairly important. So and this that article is what I read, and it's just something what I basically something what I said. So if you check the gate fidelity over time, the trace ion superconductors quantum dots has reached fidelity in past time, but the cold atoms, which is the neutral atoms, reached the fidelity of 99 to 9 at 2020. So I think it will be very important to have more further research about this. And people are also, so now it's high fidelity, with high fidelity, they are trying to solve this kind of problems, QA/OA for solving max cut, and yeah, it's showing good results. So yeah, so and one remark is why is neutral atom quantum computing is so good at this? Because the main reason is this one. This is very important, I think, because there is a huge energy gap. At the introduction, I told you that we need a huge energy gap between the real qubits and the highly excited states. And actually, there is this amount of on-off ratio between to the neutral atom quantum computing. So it can be lower the crosstalks and improve fidelity as well. So anyway, I will try to understand more about toric code and understand how it's used to neutral atom quantum computing as well. So that will be my future goal. And thank you. Do you have any question?
During the
Yes.
first thank you for the presentation.
Yes.
And this might be very basic question, but what I have learned about the quantum hardware and the analog state usually is the zero state for ground state and one excited state for one state. And but in this case, it's not work like it seems
Yeah.
not work like that way.
Right.
So is it true? What I think.
Yeah, actually, I had same question when I read that why the degeneracy is so important. Like, as far as I know, I thought it was excited state and the ground state, but it wasn't for the K-type's assumption. He is trying to make it degenerate. I don't know. I think I need to ask professor. Sorry. Yeah, I think it's I had same question anyway. Yeah. I will let you know.
And then
Yes. Yes.
Tries that more like no, I think number 4.
Number 4.
Yeah, number 4.
Yeah.
You mentioned that while emphasizing the chemical terms,
Yes.
you said those fluorides stops are get bonded and 2 others remain unbonded. And
Yes.
that's the you said emphasize it, but
Yeah.
can you explain one more time once?
Yes. Sure. So there is chemical potential between other atoms and they are bonded strongly, so they lose degree of freedom.
Okay.
As well as here and here, except the edge. Edge mode. It is the edge, yes.
So then making a strong bond makes the situation worse, right? Or is more preferable?
Yeah. So actually, we need to make it strong chemical potential to make the edge mode for the 1D superconductor.
So we're then making strong bonds is more preferable, right? In terms of using this for information processing. Yeah, I think chemical potential is important part. Yeah, maybe I can go to here. Yeah, I think yeah, I can explain further. Yeah. Thank you.
Thank you. So this is the Kitaev paper. I think it's very nice. I think you should try to read, and thank you. Do you have further questions?
It's just a random question.
Yeah.
So I think it was like one of the last slides you showed us where there are like different types of quantum computers.
Yes.
And they're like when like their fidelity listed.
Yeah.
Yeah, I mean maybe it could be a stupid question, but
Yes.
it says there's like a cold atoms quantum computer.
Yeah, so cold atom is the neutral atom.
Oh,
Yeah,
okay.
yeah.
So, yeah. Okay, then never mind. I thought,
Mm-mm.
I mean, if those were two different things, I
Ah,
was
yeah,
wondering if those two could be like,
Yeah.
combined or something, but
yeah,
if those are the same thing, yeah. That's a good question.
yeah. So actually, people use optical tweezers, which is laser cooling, to make the atoms cold for neutral atom quantum computing.
So on the left side, it says that like
Mhm.
atom temperature is still one of the limitations with
Right.
current technology. So does it mean that the cold atom is not cold enough?
Yeah. I think it's actually when you use to capture an atom, you need to use a laser array in 6 directions, and you need to adjust them very well. So I think that's the challenge for them. Yeah. Yes.
Can you go to the slide where you were talking about protected qubits or something?
Oh, protected qubits. Maybe the introduction?
With the introduction, so what is like here? Are you trying to claim that using this kind of degenerate state is not useful for a good qubit, like a good qubit candidate for quantum computing, or like can you explain a little bit more?
Yes. Yeah, actually the details are at the papers, but I think it's very nice. So um so so computation is about making qubit that is us, and qubit is a system with two nearly degenerate system, and we're going to make it avoiding the quantum decoherence. And so yeah.
Like that, tell me if I'm right. Like the coherence happens when the like loss of information in the qubit, and when those two qubits they have different energy. So if you have the same energy, does it means like the issue of the coherence doesn't exist, it doesn't exist in this kind of scenario? Like that.
Yeah. I think so. I actually searched for the meaning of the quantum decoherence because I was actually not so sure about it. And uh, in Wikipedia, it says that as long as there exists a definite phase relation between different states, the state system is said to be coherent, or else it is decoherent. So I think decoherence is something to do with phase, but I'm not sure what what it really is. Yes. Did I get the question? Like I'm not sure about what is quantum decoherence.
So the idea is like the coherence that will make this we have this kind of
Yes, that's right. Yes.
still they don't understand how
Yeah.
we have the same two energy, but
Yeah. Right.
input
Yes, actually, I skipped the explanation. Sorry. Yes. Any more questions?